So I think what I should talk about is exotic spheres a bit. And I know you've had lots of lectures on exotic spheres already, but I'll try to do it in such a way as to motivate what I've been doing. Or is it 5?
4.
4. So this will be called from exotic spheres to chain complexes with quadratic so this is of course about 1962. This was, well, 1980. So there's a 20 years gap. It started, of course, with Cavell and Milner, and in between there was this great development of surgery theory due to Browder, Novikov, Sullivan, and Wall, and then it was in 1970 was the high point with Wall's book, and then about 10 years afterwards I spent some time trying to arrange it all using chain complexes duality. So in between here is the Browder Novikov Sullivan Wall business. But let me start off with the exotic spheres. So Cavell and Milner introduced, because exotic spheres started earlier even in 1956 with Milner's examples, but the classification of by Cavell and Milner is 1963, Arnold's paper. Actually all started in Edinburgh, because both Cavell and Milner were in Edinburgh in 1958 for the International Congress, and Milner had just kind of announced, published his examples, and Cavell was a bit younger, and they started talking, and they realized that they could put the ideas together and expand Milner's examples into the kind of, well, his classification of exotic spheres. So the paper was actually called Groups of Homotopy Spheres. One, two never appeared as such. But in about 1969, Jerry Levine gave a lecture course at Brandeis, I think, and it was published in the Springer lecture notes about 1983. I was the editor of that. What happened was that I was in Paris at IHES in 1973 or 4, and I stole from IHES a copy of the lecture notes, because that was before the days of the internet, and you just had to steal things literally, not just copy them, scan them. And I was very interested in it, and no one else seemed to be interested. But so I spent 10 years looking at them, and then when the opportunity came, when I came to Edinburgh, I did have them typed up and so on. And I thought it was a big mistake to have them typed up. I should introduce all kinds of misprints. It would have been better if I had just scanned them, put them on the internet, which didn't exist then. And at least they're now available all over the place in a slightly misprinted copy. But this, what would have been in part 2 is that also on my website there's the Cavell and Milner correspondence, because about 3 years ago I went to Geneva to talk about Cavell's mathematical kind of life. He died about 5 or 6 years ago. There was a big conference a few years later in his honor in his home university town of Geneva, and together with Claude Weber and Milner himself, we looked at the letters which were there in Cavell's filing cabinet for one of them, and Milner looked at them and said, yes, we can publish them. So they're on my website also. So, and I found a wonderful Japanese person, man, whom I don't know personally, but he typed them up for us. So there's both the original and the typed version. It's Shu. Okay, so that's the background. So, and what these groups of models here, this was supposed to be a joke, a little bit. Groups means both groups algebraically, but also collecting them together. That's better explain this joke. So these groups are called theta n. So that the H cobordism classes of oriented n-dimensional differentiable, that's very important, manifolds sigma n homotopy equivalent to Sn. And for n greater or equal to, already then in 1963, known to be homeomorph. So this was, of course, the Smale, 1961, n equals 4. That was much later, of course, Friedman, 1982, and then finally n equals 3, that's 3, Perelman, 2000 something, maybe 3. Okay, so the Poincaré conjecture said that this homotopy equivalence condition was actually equivalent to homeomorphism. But there's a big difference between, well, there's no difference in all these dimensions between homeomorphism and homotopy equivalence. There's a definite difference between H cobordism and diffeomorphism. So the slide. Oops, H cobordism. What I mean is not homotopy equivalence. H cobordism we still don't know the four-dimensional Poincaré conjecture in the smooth category, but we do know that H cobordism implies diffeomorphism for n greater to 5 by Smale. Okay, so the big theorem in part 2, which was never published by Kevin Miller, but kind of conjecture, in fact, it's effectively stated in this correspondence. So it wasn't, it was known that it was known somehow, and there's some intermediate between Kevin Milner and Levine. There's also some work of Hersch and Maser. It was known in the 1960s, smoothing theory, so-called, that theta n and that in fact, I'm not quite sure whether it was known, but it's true, again, in the 5. So the methods which were used then were basically PL methods, only towards late end of the 60s, thanks to Kirby and Zimmerman, was known, all that kind of stuff was known. But we can let us look at PL. Everywhere I say homomorphism, I really mean kind of thinking is that one did in the 60s PL homomorphism, even if it is the same as homomorphism. So what is PL mod O? PL mod O is the homotopy fiber of the map from classifying space for vector bundles, the things which come from differential manifolds, and this is classifying space for PL bundles. We had lots of explanations here last November from Kirby about the difference between PL bundles, topological bundles, micro bundles, and vector spaces. But the essential difference today is between, we're talking about between BO and BPL. And it's very important that these groups are finite. So there's kind of subtle differences, but the unsubtle part is this. In fact, might as well go for broke and have the whole braid. Because it's relevant. So, somehow, philosophically, vector bundles, differential vector bundles, so to speak, or vector bundles, and PL bundles are differed by the groups of exotic spheres. So the homotopy sphere groups, exotic spheres quantify precisely the difference between differential category, PL category. Homological category is essentially the same in high dimension. It's not quite true, of course, but it's quite false, but it's a very subtle difference, just a Z2 difference. Okay, so let's have a go at so this is the thing. So this is the braid. Let's not worry about this part. We'll just worry about this part. So we have various groups. We've got the K groups of vector bundles. BG is the classifying space for stable spherical fibrations. So they are the homotopy analogues of vector bundles, and they have the very good property that the homotopy groups are the stable homotopy groups of spheres. So basically, with the transition functions for vector bundles are orthogonal maps. For PL bundles, they are PL maps. For spherical fibrations, if there were transition functions, there would be homotopy equivalences without any local structure. So if you, so there are various types. So here you have transition functions are orthogonal or linear automorphisms. Here it will be PL homomorphisms. Here you look at Sn minus 1. So it's like gluing together lots of products with S cross X. I mean, well, I'm not going to write down the whole business of transition functions, but the fibers are spheres. In this case, n minus 1s. Well, actually, this n should be quite large, k minus 1. So this would be the limit. Like that. Okay, so that's the. And these groups are also finite. In fact, that's my Sells thesis from 1951. The reason why this is finite is because this is finite. And this is finite because of Sells thesis. Okay, Owen should have had G. We're allowed to have these rather weird things here. Anything else? that's projecting. No, I can't do any. Okay, the rest are kind of not so. The loops of classifying spaces Okay, so why does one know? What does this have to do with surgery theory? Well, I don't really have. Not entirely easy to explain why, except for one striking fact, which was essentially known to, again, like so much as to Cavendish, that this weird group here, which looks just as weird as all the others, is actually a surgery obstruction group. So one of the big kind of methods for classifying exotic spheres was to implicitly prove this, that if you look at PL, so this classifies PL bundles over Sn with a fiber homotopy realization. So this doesn't seem to have much to do with manifolds. It's very unobvious. It is actually to do with manifolds once you put in Pontryagin Thom isomorphism. So we know that this is the simply connected surgery obstruction group. So the question is, what does this have to do with that, and what do these two things have to do with exotic spheres? But before I explain these things, let me just stop. All over the place. Okay, so let me just try to relate this difference between PL and G to surgery theory. So supposing we did have a let's call this, that, and this. What I mean by this, so that I'll use this for homotopy. So eta, let's have K large. So how am I going to get out of, so that defines an element in the relative group. You always, apart from the question of the initial case, you always, an element in the relative homotopy group slightly, make sure that pi n g mod pl pi n pl. Okay, there's the pl equals g. So that's an element. What is it? Now let's just worry a little bit about dimensions. Question is whether. Yeah, so this goes to Pn minus 1 PL, which is pi n of BPL. If you want, this is pi n plus 1 of BPL to BG. That's why it's n. N is right. So eta is a k-dimensional PL bundle with a fiber homotopy. Right, let's call it like, let's look at it like this, right? So here we've got the projection of the bundle. Here we have the actual projection of the trivial bundle. here we have this homotopy equivalence, H. So if you want to, maybe I should call it political. Actually, H is better. Okay. And now we're very close to, maybe I should have the H of, yeah. It doesn't really matter a great deal, but I now have to, but it's one or the other. What does matter is I have to translate this into a normal map. So this isomorphism there, which I wrote as equals, uses bundle theory to get a map from a manifold to a sphere with a bundle. So that will certainly compute that group, because we now, ever since Kevin Milner, we know what the right-hand side is. But then it also the question, how do these things relate to exotic spheres? But in any case, it's an interesting issue that the surgery theory tells you what the difference is between PL bundles and spherical fibrations. So what I want to write is this. This is the Thom space. Call this the disk. Just the quotient space. This is the Thom space of S this is Sn plus K union Sn, something like that. No, not right, Sk. So all I want to put here is that homotopy equivalence. So if you go, and now it is going the right way. So I have a fiber homotopy realization. I have also homotopy equivalence of the Thom spaces. And now I have something very interesting. You have a map from a manifold at the zero section. And this is a normal map. So this may seem somewhat, well, ahistorical. Normal maps came in the 1965, 66, with the work of Browder, after the exotic spheres, and something like that only came a little later with the work of Levine and these unpublished letters of Milner. But there's a very nice paper of Milner's called On the Image of J, where he studied exactly this kind of thing, and without using the word normal map, exactly these things appeared. So really, I thought the concept or the name was invented by Milner, and it's by Browder in a much grander context, but in the other narrow context of maps, normal maps to spheres, it does go back to Milner. Okay, so this is a normal map, and the isomorphism, so this is by contraging Thom transversality, and the map you take eta h and you take it to the Sergio abstraction. That's the isomorphism. Now, and of course we have to say what it is. Again, this is not as ahistorical as it might appear, because these groups, which were then called Pn, by Kevin Milner with first defined there, it's 1/8 of the signature of n. So if n is divisible by 4, it's no abstraction n is equal to 1. It's the so-called Kaveh-Arf invariant. So the conclusion is that if you are at all interested in the difference between PL and PL manifold theory or PL bundle theory and homotopy theory, you are forced into surgery theory. So because the groups, the relative groups between PL and spherical fibration, PL bundle spherical fibrations, are algebraic. Right? I mean, so by habit I opened top when I meant PL.
Yeah, that's true.
So I should. Okay, so this is kind of all slightly all over the place. Let's carry on nevertheless. So this is the motivation for studying surgery theory, even without exotic spheres. I will come back to the exotic spheres and then to other types, other homotopy types. But the motivation is simply if you want to compare PL homotopy, PL manifold theory, and well, things which I haven't talked about yet, Poincare complexes, but that things which arise from the quote-unquote manifold analogues in homotopy theory, Poincare complexes, but certainly spherical fiberations, then you're forced into these L groups. Now, what does this have to do with exotic spheres? Well, I've stated without much proof this theorem that theta n is the homotopy groups of PL mod O. So now let me continue on the same fine level and write out what are the homotopy groups of this braid. So we've got pi n of, let's put it over here. That's Pn. Now comes pi n L. Now comes pi n of Pg. So we know what these things are, stable homotopy groups of spheres. Now, this right? Yes. Pi n of BO, these are of course the KON groups, possibly with, well, reduced or something like that. But that has to do with topological K-theory of vector bundles, the kind of things for which there's Bott periodicity. So it's kind of, the late 50s was well known thanks to Bott. This are the groups which claiming without much proof, today at least. And then what's left over here is pi n of G mod O. And here we have and now, so the braid doesn't extend in some kind of, you have to kind of invent ever more complicated classifying spaces or ever more complicated loop spaces to the left or classifying spaces to the right. And then of homotopy groups, it does kind of close up on itself. Now, in what sense, what is the map here? This is the map called B. And the image of B is called BPN. And it goes on to, in theory, like that. But in fact, this map is not quite zero. Let's get this slightly right. I've got it wrong, of course. What I need to have is like that. Pi n minus 1 of BO. And here I need pi n minus 1 of G mod O. And this is now.
What is PN and BPN?
Where? PN
Yeah.
is just Cavell-Milner's name for Ellen. So why did they call it PN? And in fact, this has a name called AN. Let me just finish this. I'll try not to make a mistake, so just simply let this. But the important map here is the B. And the reason why this map is called B and why this sub is called BPN is that these are the exotic spheres which bound framed manifolds. And the map B, this map here, takes an exotic sphere and sends it to the tangent bundle of the tangent bundle. So an exotic n-1 dimensional sphere has an n-1 dimensional tangent bundle, and it's a stable tangent bundle that matters. And in fact, this is always 0, I think. So this means that this map is on to... there's a simplification here which I've lost at the moment. But one can write down the co-kernel, but I think the co-kernel, this map is 0, this map is... Now various maps which there's one map which is onto. Okay, better not makes... Better to say this should have been 7, not a mistake. That's serious. Now, what I want to explain is what the... well, first let me just state what the maps... Firstly, why does one get exotic spheres to be that? And the answer is that an exotic sphere has a stable tangent bundle which is got a PL homotopy realization. Okay, so that's a very important. So this isomorphism so this very much uses the Smale H. Orden theorem. The order in which things were proved is actually very interesting. I think tools appeared at just the right time. It was kind of very amazing. Okay, so let's look at, so I defined that. Unfortunately, I've lost the dimension, but in a systematic way. The stable So that means that sigma goes to VO, goes to VPL, just like I had before, given by the PL homeomorphism given by Smale. So using everything, using the manifold kind of H-Rosen theorem and the bundle theory and the connection. So that's an isomorphism. And the map back is the thing which I've just erased, the back by the programming clock. Sort of. Be a bit careful. It's not quite right what I said, because you have to, not entirely clear that that surge abstraction is 0. It must be a low, but it is. So what we've got here, lost a little bit of, yeah. this group is the thing which I called AN minus 1. And this group is called the one which is PN minus 1. So what I need to explain now is the manifold interpretations of this sequence. These are almost framed manifolds. That's why it's called A. But they're closed manifolds, whose tangent bundle is stably trivial except at a point. So almost framed. N-dimensional manifold. Basically, what AN is n-dimensional framed n-dimensional manifold with boundary. With homotopy sphere boundary. I should call them W. So the map here is the Sergio abstraction. So if you've got such a thing, and now we're again being slightly ahistorical, because normal maps did not exist, but it is true that there's a more or less obvious degree 1 normal map. What you have here is some kind of bundle which is a PL realization. So the map from here to here is given by the Sergio abstraction which used to be here. There was 7 like that. Now, it's all slightly involved, it's very snaky, but it is the right picture. And what W, so if you've got some, here you've got a normal map. Let's call this not F, F big B. This is F. So this is the way in which these groups were computed. One knew from, basically from the work of Bott. This map is the J homomorphism. So Bott computed these groups. Adams computed the image of J. So in the 1950s, 1955, Bott, 1961, Adams, and then in 1962, it was so new that the reference to Adams that wasn't even published yet, but didn't net it. A few years later, it all appeared. It was given an amendment. And then there was, of course, Smail in the background. So this group was computed using the fact that one can compute what this is. Combining the work of Bott and Adams, one knew what this was. They themselves computed this group. And so this left a nice exact sequence which worked out what this is. And the first example was this. So next time, I'm afraid there will be a next time, I will explain how to throw chain complexes at this. This is all very much the homotopy theory and bundle theory, but not really Sergio theory except here. Okay, that's it for today. Thank you. How did I start late?